Alright, so we're going to get started here. Today we're looking at chapter 9.3 on alcohol. So we have looked at hydrocarbons, we are looking at alkane, alkyne in the last few lessons. Today we are looking at another functional group. So there is something known as alcohol. So that's something that we are going to discuss for today. So before I move into alcohol itself, it says here functional group while carbon atoms are covalently bonded only to other carbon hydrogen atoms in alkanes, alkene, and alkynes. It is possible for carbon to form covalent bonds with other atoms or groups of atoms known as the functional groups. And it says here functional groups is an atom or group of atoms that give a characteristic set of chemical properties to a molecule containing those atoms. See, a homologous series such as alkenes, alkynes, alcohol, carboxylic acid, and esters are categorized as the presence of a particular functional group. If you still remember, when we were talking about alkene previously, we are talking about presence of a double bond. If it's alkyne, it's the presence of a triple bond. So today we are looking at alcohol. If you come across alcohol, there is this presence of the same functional group in each of these alcohol compounds. So I will show you in the next few slides. Alright, so we're going to look at this particular table here. You can see these are the different homologous series that are present, and all of these consist of 2 carbons. So if it's alkane, you have ethane, which also have 2 carbon. So you have 2 carbon and 6 hydrogen. If it's alkene, you have ethene, also you have 2 carbon and 4 hydrogen. If it's alkyne, you have 2 carbon and 2 hydrogen. If it's alcohol, you have 2 carbon, 6 hydrogen and 1 oxygen. Carboxylic acid, you have the formula, which is CH3COH. Ester, which is methylmethanol, you have HCOOCH3. So the point here is that you can see the difference in terms of their use. If it's ethane, you can see ethane is found in natural gas and is used commercially to produce ethene, from which many plastics are made. Ethene is a gas from which is an important natural plant hormone. It is used in agriculture to force fruit to ripen. And then you have alkyne. Ethane is a gas used for oxygen for welding. You have alcohol, which is what you normally find in alcoholic drink. So if you look at, let's say, beer, or the production of beer, or you're talking about production of wine, they normally generate alcohol from the fermentation of plant or yeast products. If it's carboxylic acid, it's ethanol acid dissolved in water to form vinegar, giving its distinctive sour taste and pungent smell. If it's ester, you have methylmethanol, is a clear liquid with strong present odor. So if you come across, let's say this is artificial flavor or artificial smell, most likely that particular compound is made of ester, and it actually produces a particular strong smell, and it's artificial, so you do not need to use the actual product to create your artificial smell. For example, you come across candies, or you come across perfumes, and we know that some candies or some perfume, they use artificial smell and taste. So what they normally do is that if you come across a product and says that it consists or it contains artificial banana smell, that particular artificial smell does not come from actual banana, it actually comes from ester itself, which is a type of chemical that can be generated in the lab. Moving on to the next slide. Alright, so continue on this particular side. When we are talking about alcohol, it says that the functional group in alcohols is made up of 1 oxygen atom bonded to a hydrogen atom. It says that this OH group is known as hydroxyl group and replaces 1 hydrogen in the structure of an alkane. Successive members of this homologous series differ by CH2 unit. This is when naming alcohol, a similar systematic naming process. So the one used by alkenes, and alkynes applies. It says that the number of carbon atoms in the molecule is indicated by the stem name, so you have add per boot, but the surface is always OL. For example, if that particular alcohol structure consists of 1 carbon, then what you have is methanol, CH3OH. If you have ethanol, it consists of 2 carbon, but it ends with OH in that particular structure, and the name it ends with OL. So all of the alcohol compounds must end with OL. That's something you must make very clear. So if it's 1 carbon, methanol, 2 carbon, ethanol, 3 carbon, propanol, 4 carbon, butanol, 5 carbon, pentanol, 6 carbon, hexanol, 7 carbon, heptanol, 8 carbon, octanol, 9 carbon, nonanol, and 10 carbon decanol. So that is how it is. Moving on to the next slide. Alright, so based on this diagram, we have done this many times. When we are talking about the structure of alcohol, you have your electron dot, which is your Lewis structure. You have your structural formula. Bema structural formula is very similar to a valence diagram. The only difference is the structural formula does not show the lone pair electrons. And then we have the condensed structural formula, which is without the bond. So something for you to think about. So once again, if you have methanol, and these follow a formula, and I'll give you a formula right now. The formula that it follows for alcohol, you have C, you have N, so the number of carbon that you have, H, which is the number of hydrogen, so CnH, 2N, plus 1, OH, which is the formula that you're going to base it on. So the formula of alcohol is Cn H2n plus 1 OH. Cn H2n plus 1 OH. Alright, once again, if you look at methanol, we know that the number of carbon that we have in methanol is 1 carbon. Hydrogen will be 2n plus 1. 2 times 1 plus 1, you get 3. So you have CH3OH. If you have ethanol, you have C2H5OH, so number of carbon here will be 2, number of hydrogen will be 2 times 2 plus 1, we get 5, and then you get OH. Propanol will be C3H7OH, number of carbon will be 3, number of hydrogen will be 2 times 3 plus 1, we get 7, C3H7OH, as you can see here. So this is a general idea of the structures of methanol, ethanol, and propanol. As you can see, once again, there's different ways of drawing the structure of that particular alcohol structure that you have. So if it's methanol, and when you draw it, your structure is CH3OH, and that applies to electron dot, structure formula, and the condensed structure formula, and then ethanol will be C2H5OH, propanol will be C3H7OH. So something for you to think about. Moving on to the next slide. So if I show you this diagram here, you see many of the small alcohols are useful as fuels. Ethanol can be used as a fuel on its own or mixed with petrol. You see, the combustion of ethanol produces carbon dioxide and water. So if you recall, ethanol, along with the hydrocarbons that we have discussed previously, the hydrocarbons that we have, which are composite consist of carbon and hydrogen. So you have alkane, and alkyne, those are hydrocarbons. So when you're burning with the presence of oxygen, it releases carbon dioxide and water, very similar to the combustion process in alkane and alkene. The only difference here, when you're talking about alcohol, it consists of OH as its functional group. So so it contains one additional oxygen as compared to an alkane structure. So something for you to think about. Move on to the next slide. So the oxygen in that particular ethanol compound. If I show you this particular slide here, it says the boiling points of alcohols increase as the size of the alcohol molecule increases. However, the boiling points of the alcohols are all higher than those of the corresponding alkanes. All of the alcohols are liquids at room temperature. In contrast, in the alkanes and alkenes, many of which are gas. The higher boiling points of alcohol is due to the presence of OH group, which allow hydrogen bonding to occur. Something you have to be very clear about. When we were talking about hydrocarbons, alkane, alkene, alkyne, there's something common between alkane, alkene, and alkyne. That all of them only have one type of intermolecular forces, which is a dispersion force. If you're talking about alcohol molecule, you're talking about it being polar as compared to hydrocarbons, which are non-polar. So alcohol in this case is a polar molecule. So alcohol being polar contains more than one type of intermolecular forces. It has the dispersion force. It also has the dipole-dipole and the hydrogen bonding. So it has 3 different types of bond. Once again, it being polar, and it has, once again here, based on what we have discussed previously, there's a covalent bond between oxygen and hydrogen. And at the same time, because it is polar, it has dipole-dipole, and it has hydrogen bonding because of the covalent bond between hydrogen and oxygen, and it's also having lone pair electrons on that particular oxygen atom within the alcohol structure, and we know that that structure now is capable of forming a hydrogen bond. In general, hydrogen bonding is 10 times stronger than dipole-dipole, and having hydrogen bonding will enable it to definitely have a higher bonding point as compared to alkanes, alkenes, or alkynes. because if you are talking about hydrocarbons, therefore alkynes, they are non-polar, which means they only have dispersion force as an intermolecular bonding. In this case, because this particular alcohol structure contains hydrogen bonding in addition to the intermolecular bond, it actually strengthens the intermolecular bonding, which means the boiling point will be a lot higher. So you can see that when the number of carbon increases on this particular diagram on the right, when the number of carbon atoms increases in the alcohol molecule, the boiling point increases. At the same time, you can see that the boiling point of alcohol will also be greater than the boiling point of alkene or alkenes because of the presence of hydrogen bonding, which is a type of dipole-dipole bond that will strengthen the intermolecular bonding of that particular structure. Moving on to the next slide. So it says here, hydrogen bonding also influences the solubility of the alcohols. The presence of OH group allows hydrogen bonds to form between water molecules and alcohol molecules. For the smaller alcohols, such as methanol and ethanol, this allows the alcohol to dissolve readily in water. The solubility of other alcohols decreases as the length of the carbon chain attached to the OH group increases. It says a longer carbon chain means that more of the molecule is non-polar and the molecule becomes less polar overall. So what this is trying to tell you is that the hydrogen bonding will affect the solubility of that particular alcohol structure. Generally speaking, alcohol can dissolve in water, unlike alkene, and alkyne, which are not soluble in water because of the difference in polarity, and as you're probably aware, water is polar. So the point here is that if that particular structure can form hydrogen bonding with water, it will dissolve in water. But when you increase the number of carbon within alcohol itself, we know that when the length of carbon chain increases, the solubility of that particular structure in water will reduce because that particular molecule becomes less polar overall. So as you can see in this particular diagram here, hydrogen bond can form between water molecules and in this case, the methanol structure. But something that you have to bear in mind, by the solubility of that particular methanol structure, if compared to the solubility of ethanol, propanol, butanol, the higher the number of carbon within that particular compound, the lower the solubility of that particular compound in water. Something for you to think about. So move on to the next slide. So it says here, structural isomers of alcohol. We have discussed structural isomer previously when we talk about alkanes and alkyne. Structural formulas or structural isomers are molecules that consist of the same molecular formula or contains the same molecular formula but different structural arrangement. So structural isomers of a molecule are molecules that contains or consist of the same molecular formula but different structural formulas. So structural arrangement. So it says that the position of hydroxyl functional group influences the chemical and physical properties of alcohol. Alcohols with more than 2 carbon atoms have more than one position where the hydroxyl functional group may be. For example, hydroxyl group in propanol can be bonded to the first or the second carbon atom. This gives 2 different molecules. So you either have CH3, CH2, CH2OH, or you have CH3, CHOH, CH3. So there will be different naming as well. And something for you to bear in mind, these are structural isomers of one another because even though they have the same molecular formula, but they have different structural arrangement. There's a reason why they are structural isomers of one another. See, the name of the alcohol must reflect the structure of the molecule, so a system of nomenclature is used. So moving on to the next slide. Alright, so continuing what we have discussed previously, it says here to name an alcohol, start with the name of the parent alkane, remove the E from the N and add the suffix OL. It says the atoms in the longest carbon chain are numbered from the N that is closest to a functional group. The number of the atoms to the hydroxyl group that is bonded is to be shown before the OL ending is separated by hyphen. So something for you to think about as well. When you're naming alcohol, the ending part of the alcohol will be OL instead of any other alphabets that you use. Which means that all alcohol structures will end with OL because they are of the same homologous series. Move on to the next slide. So if you look at this particular example that is being given in the textbook, you have this particular structure that consists of 3 carbon. And we know that if it consists of 3 carbon, it will be propanol, and in this case, this is known as propan 1O, because oxygen O, in this case oxygen, is on the first carbon. Can we see that? If I'm going to highlight this for you at the top, oxygen is on the first carbon. Because it is on the first carbon, we know that the naming here will be propan 1O. So I need to try out the second example. Here, just a clue to you, the oxygen on the second example here is on the second carbon. Can you see that? Oxygen is on the second carbon. So something for you to think of. So what do you think is the name of the particular structure? Think about it, and then we discuss more in class. Once again, give you a clue here. It should be propan, it should be O, but in between, because the OH is on the second carbon, so it should be 2. So think about it. And when you're naming, make sure that you do not leave any gaps within the naming itself, that it should be of one word by itself. Something for you to think about as well. Moving on to the next slide. Alright, so this is the final slide. We're just going to wrap it up and finish this particular slide here. So if you look at the example given at the top, the longest unbranching here consists of 4 carbon. Bear in mind, if it contains a side chain, what you need to do here, and if it contains contains side chain and it contains the hydroxyl functional group, what you do, you have to prioritize the hydroxyl functional group here. So you know the hydroxyl functional group is on the second carbon, and then you have the side chain on the third carbon. So what you need to do here, when you're naming, you have to name the longest unbranched, which is butano, and we know that the second carbon is where hydroxyl group is present, and the third carbon is where the methyl group is present. So what you need to do with this particular naming here, once again, you have to prioritize the hydroxyl group. So your naming has to be 3-methyl butan 2O, 3-methyl butan 2O, which is the name of this particular structure. So once again, you have to find the longest unbranching, prioritize the hydroxyl group. So in this case, hydroxyl is on the second carbon, and the third carbon is where methyl is present. So you have 3-methyl butan 2O. Alright, so I need to work on this particular example at the bottom. So you have to find the longest unbranching, and that consists of 5 carbon, and we know that 5 carbon is pentano, and we know that the location of the hydroxyl is on the third carbon. So most likely your name here has to be pentan 3O, and then you can identify the methyl side chain on the second and the fourth carbon. So your name here could be, let's just say 2,4, because the methyl is on the second and fourth carbon. So you have 2,4 dimethyl, 2,4 dimethyl, pentan 3O. So think about E, so 2,4 dimethyl pentan 3O, and see whether you agree with this answer. We will discuss more back in class, so email me your question if you have any, and then we'll discuss more questions as well if you post it on social stream, or you can also ask me a question as well in class. So I will see you then.